Here we're going to be investigating the interpretation of a confidence interval for mu. The interpretation of a confidence interval for a parameter is one of the most important things that we need to know in an introductory statistics course, so let's get on with it here. So first of all, we view that parameter mu, the population mean, as a fixed, typically unknown quantity. We do not know what the value of mu is, and we want to estimate it. That is the whole point of doing a confidence interval. But it is an unknown quantity, it is sitting there, and we are trying to estimate it, and we do so with our sample mean. But we use our sample mean and some mathematical theory and some assumptions to calculate this confidence interval. And we've looked at this before, this confidence interval for the parameter mu when we're sampling from a normally distributed population where sigma is known. So we go through, put everything through our formula, and we get an interval. Let's say we find a 95% confidence interval of 4.8 to 22.7. Now what does that mean? Interpreting this is the most important bit. Calculating it, easy stuff, and typically done by a computer anyway. So we want to come up with the proper interpretation of that interval. Well, in simple terms, we often say something like, we can be 95% confident that the parameter mu lies within that interval. Except this is a little bit unsatisfying, to me at least. 95% confident? What exactly does that mean, 95% confident? Well, in statistics terms, we usually phrase it another way, and this other way is a little bit more confusing. So we say things along these lines. Suppose we were to repeatedly sample from the population and calculate a 95% confidence interval for each sample. So we're repeatedly sampling from the population, calculating a 95% confidence interval for each sample. Now we don't actually do this in practice, but just conceptually, if we were to do this, then 95% of those 95% confidence intervals that we calculate would capture the true value of the parameter mu. So let's look at this visually. So here we have mu sitting here, a fixed value, and that line above mu is just representing it sitting there fixed. So I could go through and get a sample and calculate a confidence interval, and suppose I do that, and there it is. So I get this, and this value here is my x bar. The dots representing the x bar, my midpoint of the interval, and over here is my upper bound of my 95% confidence interval, and over here I'm having this as my lower bound of my 95% confidence interval, and this particular interval actually captured the value of mu. So mu is found within my interval between my lower and upper bounds. Now what I could do is go and get another sample from my population, and I would get a different interval because x bar would vary from sample to sample. So here my sample mean has changed, but this particular interval still captures the value of mu. And I could do it again, and that interval captures the value of mu. And we know from the theory that 95% of intervals calculated in this manner would capture the value of mu. And oh, here we go. Here, this is an extreme value of x bar. What happened here was that we got an unusual value of x bar, and the resulting interval was off to the left and did not capture the real value of mu. Now we're not going to know whether this takes place or not when we're actually taking a sample, but we know from the underlying theory that 95% of the intervals calculated in this manner will capture mu and 5% will not. So let's repeatedly sample a few more times. We could just keep on going and keep on going and keep on going like this, and if we were to repeatedly sample from our population, we know that 95% of the intervals calculated in this manner would capture mu. So in the real world, we only take one sample and we get one confidence interval. And we don't know whether our interval is one of those 95% of the intervals that capture mu, or whether it's one of those 5% that happen to miss just due to chance. But we do know that our interval should just be like a random sample from all of these possible intervals, and so we can be 95% confident that it was one of those intervals that captured mu. So let's look at an example. Suppose we take a random sample of 10 graduating students from a large high school and get their scores on the SAT exam. And for the sake of argument, let's just say all graduating students at this particular high school are writing the SAT exam. We go through and we get a mean score on the SAT for these 10 students of 1240 with a corresponding 95% confidence interval for mu of 1160 to 1320. Now note first of all that 1240 lies right in the middle of that particular interval, and we are going plus and minus our particular margin of error in this case. 1240 plus or minus 80, our margin of error happened to be in this particular setting, and we're 95% confident of what? Well, we're 95% confident that the population mean SAT score for graduating students in this class lies between that 1160 and 1320. Now, from the other perspective, from the repeated sampling argument, we could say in repeated sampling, 95% of the 95% confidence intervals calculated in this manner would capture the true mean SAT scores of graduating students in this class. But we have one of those intervals, and if 95% of the intervals capture mu, and we have one of them, then we can be 95% confident that our interval was one of those that would capture the true value of mu. Now, there's a lot of ways of misinterpreting this, so let's look at a few of those. A few misconceptions that are just flat out wrong. Can we say that 95% of students in this class have SAT scores that lie between 1160 and, what? 1320? Well, can we? No, we can't. We're not saying anything about the percentage of students in this class that fall between those two values. We're talking about the population mean. And so this is just flat out wrong. We cannot say that kind of thing. Can we say we can be 95% confident that the sample mean SAT scores of the 10 students lies between that? Sample mean falls right in the middle of the interval. No, and we're not making statements about the sample mean. No, this is just flat out wrong. We're saying something about the population mean. Can we say that in repeated sampling, 95% of the intervals will capture the sample mean? Again, we're saying the sample mean, and no, we're not talking about the sample mean. We are sure that our sample mean of our one sample falls right smack dab in the middle of our interval, but even those different sample means from those repeated samples in the repeating sampling argument, we're not going to capture 95% of those. It doesn't work like that. So we're talking about the population mean, and so here, this is just flat out wrong. So make sure you get this down. The interpretation of a confidence interval is a very important thing.